Welcome to Module 18, Boiler and Heating Water Plant Control. In this module, we focus on how a BAS coordinates heating demand, pumps, valves, boiler enable, supply temperature reset, staging, shutdown, and recovery without crossing the safety boundary of the boiler or burner management system. Boiler control must maintain safe flow, stable temperature, combustion protection, and useful return water conditions before it pursues efficiency. The goal is a heating plant that is safe, reliable, efficient, and understandable to operators. The objectives are practical. You will define boiler plant startup, staging, shutdown, and recovery. You will coordinate pumps, isolation valves, proof points, and boiler enable. You will apply outdoor air reset without violating coil needs, domestic or process requirements, boiler limitations, or return water protection. You will distinguish condensing and non-condensing return temperature concerns. Finally, you will commission plant modes while respecting the boundary between BAS coordination and burner management safety. The core concept is that heating plant optimization must stay inside equipment-specific boundaries for flow, temperature, combustion, and safe recovery. A boiler plant is not successful because the BAS enables a boiler. It is successful when the correct heating demand is proven, safe water flow is established, temperature is controlled inside the equipment range, and local boiler safeties remain authoritative. Efficiency strategies such as outdoor air reset and lead lag are important, but they come after safe and reliable plant operation. Start with control boundaries. The BAS supervisory layer normally manages schedules, demand aggregation, resets, lead lag, alarms, trends, and operator interaction. The plant controller or field controller handles pumps, isolation valves, proof, enable logic, setpoint delivery, and fallback. The boiler or burner management layer owns flame safeguard, combustion protection, internal safety timing, and manufacturer-specific limits. The physical process is the water, flow, temperature, and load. A strong sequence makes this ownership visible. Heating demand can come from outdoor conditions, heating valve requests, zone demand, process demand, schedules, or a combination. The sequence should not start and stop a plant from short, noisy, or invalid signals. Demand should persist before startup, and it should clear only after the plant need has been reduced for enough time. It is useful to separate demand from permission. Demand says heat is needed. Permission says pumps, valves, flow proof, safeties, and equipment readiness allow the plant to start. Outdoor air reset commonly lowers heating water supply temperature during mild weather and raises it as outdoor temperature falls. For example, a plant may use 180 degrees at 10 degrees outdoor air and 120 degrees at 60 degrees outdoor air. At 35 degrees outdoor air, linear interpolation gives about 150 degrees, but the calculated value is only an initial set point. The sequence must enforce approved high and low limits, protect coil capacity and recovery, and respect condensing or non-condensing boiler requirements. A safe startup sequence proves the water path before asking the boiler to fire. Demand persists, isolation valves or paths move to the required position, pumps start. Flow or differential pressure is verified. Only then does the sequence enable the lead boiler and release temperature control. Shutdown also requires a defined order. Some systems need pump overrun or heat removal. Some valves close immediately, while other functions remain active for protection. Every waiting state should have a timeout and a defined recovery path. Boiler staging should use more than supply temperature error. Stage-up evidence may include running boiler loading, supply temperature error, rate of recovery, persistent demand, and available capacity. Stage down should confirm that the remaining boiler can maintain the target without rapid restaging. Minimum runtime, minimum off time, and interstage delay reduce cycling. Lead lag should consider availability, maintenance release, runtime, starts, efficiency, capacity, faults, and sometimes fuel availability. Boilers require approved flow through the heat exchanger. Pump command is not enough proof. Depending on the plant, proof may come from pump status, differential pressure, flow measurement, isolation valve position, or equipment feedback. Return water temperature also matters. Condensing boilers can gain efficiency when return temperature is low enough, while some non-condensing boilers need protection from sustained low return temperatures. The sequence must reflect the installed boiler technology and manufacturer limits. The BAS should never replace burner management, flame safeguard, fuel safety, or pressure vessel protections. It can coordinate plant demand, set points, pumps, valves, alarms, and trends, but approved local safety functions remain authoritative. Steam and heat exchanger interfaces add pressure, condensate, warm-up, trap, and water hammer concerns. BAS logic should coordinate the heat transfer process while respecting factory high limits, approved safeties, and the requirements of the local equipment. Failure recovery must be explicit. If the lead boiler fails, the sequence should stop its request, maintain required flow as appropriate, select available standby equipment, prevent simultaneous uncontrolled starts, and report the capacity impact. Following power restoration, staged restart helps protect electrical demand, fuel systems, and hydronic stability. Manual operation also needs rules. Operators should know what remains automatic, what is supervised, what is locked out, and what must be documented before returning to normal. Use this checklist before approving boiler plant logic. Document the boiler type and manufacturer limits. Confirm demand is persistent and valid. Confirm reset bounds. Require flow proof before boiler enable. Stage from loading, temperature response, and timers. Make lead selection account for maintenance, availability, runtime, and faults. Match return water requirements to the installed technology. Review steam or heat exchanger interfaces where present. Test failure recovery and staged restart. Keep combustion and burner safeties under approved local control. Let us summarize. The BAS coordinates demand, reset, pumps, valves, staging, alarms, trends, and operator visibility. Boiler and burner management safeties remain local and authoritative. Heating water reset must be bounded by coil capacity, recovery, boiler limits, and return water requirements. Boilers should be staged from verified capacity evidence with minimum runtime, minimum off time, and interstage delay. Finally, failure recovery must include standby selection, stage restart, alarms, fallback, and tested reset behavior. In the next module, we move into pumps, differential pressure, and minimum flow control.